Hi, welcome back. This time we are going to discuss the hybrid pi model for the metal oxide semiconductor field effect transistor MOSFET. In the previous model, we talk about the hybrid pi model for the BJT. So do refer to that because we derived a very good insight from that tutorial and we understood various different parameters. So this time it is pretty same with what we talked before. So here is an equivalent circuit. MOSFET is a three-terminal device with a gate, drain, and source. So G stands for gate, S stands for source, and D stands for drain. So with respect to just like your BJT, you have three configurations. For BJT, you have common base, common collector, and common emitter. Similarly, for the MOSFET or JFET, you have three configuration in which the circuit can be biased. The transistor can be biased. So for the FET, you have common gate, one CG, common source CS, and common drain CD, three types. This is common source because the source is taken common with respect to gate and drain. So the input side of this circuit is gate to source, output side of this circuit is drain to source. So you have a parameter called as GM, which is transconductance. When we talk about transconductance, it is a ratio of output current by input voltage. So it's a particular type of a gain. So your output current is ID, input current voltage is VGS, and output side of the circuit kept as open. That is VDS is equal to 0. For VDS is equal to 0, you have this ratio of current over voltage. That is your transconductance. Remember, I'm using the small letters. It means I'm referring to the AC model. This is an AC model and AC analysis. So when you do the frequency analysis of a circuit, you need to interpret your device behavior in terms of this equivalent circuit or model. And that's why we call it as a model. And in particular, we call it as a hybrid pi model. Another way, for a DC biasing condition, the GM can be defined as a ratio of 2 times ID divided by VGS minus VTS. So you see the capital letter and underscore the DC analysis, just like you connect the DC voltage sources to your MOSFET and bias it to set the operating point. So that's how. There is a this VGS minus VTH is called as VOV, which is an overdrive voltage. So overdrive voltage is the difference between these two. VGS is your input voltage between gate and source, and VTH is your threshold voltage, the voltage required to invert the channel of the MOSFET, that is threshold voltage. Now, final parameter is your output resistance RO, which is a ratio of voltage by current. It is output resistance, therefore it is a ratio of output voltage divided by output current by keeping input voltage across gate and source to be zero. So again, the small quantities indicate this is an AC analysis quantity for the AC analysis. Take a reciprocal of RO, you get output conductance. So here you see the circuit, your VGS is applied between gate and source, small VGS, and the output side is your output resistance. And you have this dependent current source that is coming from which is the drain current. Drain current is given as GM times VGS. Okay, so GM will be drain current divided by VGS. So this drain current flows through RO, creating a drop across the resistance RO, which is your output voltage. So we'll just try to see what value you get. So for example, this is your ID, and this ID flows like this, creating a drop like this. Okay, so we say that VDS would be minus ID times RO, which is minus GM VGS times RO. This is your VDS, small letter. We are talking about the AC, and then VDS divided by VGS. That is the voltage gain, which is minus GM times RO. So that's your voltage gain. This is your voltage gain of the MOSFET. This is your cross section of the MOS transistor. You have 3 terminals, and this is an N channel because you have the P substrate in which you have 2 doped N plus channels, and this is your channel, and you say that the current is saturated, indicated by the dashed line, saturated region of the operation. This VDS is indicating the electric field across drain and the source. So there is one more parameter where your output resistance is a function of channel length modulation, and channel length modulation indicated by lambda is important because it decides the MOSFET output resistance RO in the circuit design of when you design current mirrors, amplifiers, and other circuits. So very important quantity. So hope you enjoyed this short tutorial about deriving an equivalent hybrid pi model for your MOS transistor. And this is for the common source configuration. Exercise for you would be to get it for common gate, and common drain configurations. Just make the drain or gate common and just draw the model. So that's an exercise for you. Stay tuned for more informative content like this. And if you like this video, click like button, subscribe button, and share it for wider reach. Wish you happy learning.